taught you about how to fabricate the nanoparticle. Combustion method he has explained you. In the same line, I am going to tell you about the various kind of synthesis method that can be used to prepare the nanoparticle. Yesterday we have seen the size, shape of nanoparticle, as well as we know about the basic of nanomaterial. So far now you already understand the basic about nanoscience, nanotechnology, their shape, size, and various types of nanomaterial. Today's topic is about synthesis methods. But to begin with today's lecture, let's have some revision what we learned yesterday. Please see the question carefully and try to answer yourself. Okay? If somebody knows the answer, of course he can give the answer. So please read. There are few questions, 6 to 7 questions. I am going to display one by one. The first question: which one of the following is an example for semiconducting nanowires? Silicon. Silicon is considered as a semiconductor material. If you see nickel and platinum, these are pure metal, so they are not semiconductor. So here answer is silicon. Yesterday I told you about matter, or their band gap also changes. Depending on the band gap, we have classified the material as semiconductor, insulator. So if the material is semiconductor, it has certain band gap. If the material is metal, they have small band gap. So the answer is silicon. Who discovered nanotube? So yesterday you have seen nanotube. I have shown you one of the pictures, and in that picture there was carbon nanotube, multi-wall, double wall, and I also told you about the carbon. If you remember, carbon is versatile material. We have seen various allotrope. Carbon nanotube is one of the allotrope of this carbon family, and this carbon nanotube was first discovered by Japanese scientist Sumio Iijima. This carbon nanotube was in the picture until graphene has been discovered. So 1991 to 2005 or 2010, almost 20 years, lots of research has been done on carbon nanotube. And it was, we cannot say replaced by, but most of the researcher has moved their research topic from carbon nanotube to graphene due to the graphene property. However, in some cases, carbon nanotube is equally important. So the answer is Sumio Iijima. Which of the following is an example for electrical property of nanostructures? Which property is a part of electrical property of a nanostructures? Both single, melting, or from this side? This one? This one? tunneling, both. Which one of the okay, which one of the following is an example of conduction? Okay, so in conduction, what is current means? It is electrical property. So what happened when we talk about electricity, electric current? It's about the movement of electron. Okay, so it jumped from one region to another region, valence band to conduction band. So when there is a movement of electron, that is tunneling. It's a kind of movement of electron. So same thing happen in electric current also, but tunneling is a different phenomena. It is related to the electricity. If you heard about quantum tunneling, when electron move, if you apply certain kind of electric field to the material, then electron jump from valence band to conduction band. So depending on how much voltage electric field you are applying. This is the same concept in television we have used. We have electron gun and we apply some electric field, and then electrons are generated and they strike the screen and you can see the image. So the tunneling current. I think yesterday professor might teach you, so most of you already know, but if you remember, there might be sometimes confusion about abbreviations. So what is SEM? Sometimes we say SEM. This one. Fourth one, okay. Scanning electron microscope. How to remember it in simple? Because in SEM, electron is used. So you should remember this keyword, okay? So you will never, because scanning electron microscopy, yesterday Professor might taught you about this. So electron is used, it strike on the sample, and then again it was detected by the detector, you can see the image. So the answer is scanning electron microscopy. Sorry. This one. Which one of the following is an example of zero dimension? Zero. So yesterday we learned dot, two dot connect line, two line connect, two dimensional, two dimensional, two dimensional, two sheet connect, three dimensional. So that way, nanoparticle. Very easy again. Who defined the term nanotechnology? Okay, so Norio Taniguchi. This yesterday we have seen, he was working on the microscopy, electron microscopy, and he's the first person who used this term as a nanotechnology. So the answer is Norio Taniguchi. Which of the following is an example? Sorry, what happened? Okay, is an example of one dimension? Nanorods, line, wires, lines, okay, line, wires, or rods. So it can only extend in one direction, this or this. It cannot extend or increase or expand or grow in another two direction. Only one direction, so it is one dimension. And what is the example? Nanowires, nanorods. Okay. So always remember, one dimensional means something like rods, wire, rope. and two-dimensional means sheet like structure, like paper. Just imagine you are holding paper that is two-dimensional. So it is very easy to understand. Particle, zero dimension. Rods, wire, one dimension. Sheet like structure, two dimensional. Cube, spheres, three dimensional. So that was the revision of the yesterday's class. Now let's move to the today's topic, how to create the nano particle. Yesterday we have seen various type of shape and size, like three-dimensional structures, two-dimensional structure, one-dimensional and zero-dimensional. How to create, how to fabricate these materials, what are the technique, and whether we can use the bulk material to create two-dimensional, whether we can create one-dimensional using two-dimensional, zero-dimensional using one, and from zero dimension we can create this three-dimensional. Is it possible? Let's see. You want to create a small particle that we call as a nanoparticle. Now, so far there is no machine that you put something big and it come out with a small structure. There is no shrinking machine. Okay, like you put gold bar in certain machine and you can see powder is coming out in a second. There is no such machine available. Future we don't know, but at this moment there is no shrinking machine. Or you can press it and it become very small. So since shrinking machine is not available, we have to create the nanoparticle in the laboratory using various technique. And this technique is depending on our desire for creating the nanoparticle. What type of nanoparticle we want to create? Each technique has some disadvantage, some advantages, and your application area is important. What kind of nanomaterial you are looking for? According to your desire of creating the nanoparticle, you choose the synthesis methods. So when we think about creating the nanoparticle, we have to create in the laboratory. So those creation of nanoparticle can be done two ways. Again, I think yesterday you might have seen this slide. I'm not going to tell more detail. Yesterday professor already has shown one or two slides, but let's look at quickly. There are two approaches. One is top to down, okay? Like you are on the top floor and you are coming on the down or first floor or ground floor. So that is starting from big, like if you want to make some kind of small statue and there is a big stone, you can carve it and make a small kind of structure. So started with big and end up with the small. So that is top down. Another technique is bottom up. So bottom up, you start from very small particle and then you create a bigger size. Like you might play Lego when you was small. You play with the building block or Lego. Those kind of game, you start with very small pieces and end up with certain structure. So that is bottom up. From zero you start and you create something. So nanomaterial can be synthesized two ways. One way is from larger size to smaller size, top down. And another, you start with very, very small size. It may include chemical reaction starting from atomic level. And then you ends with various kind of nano shaped particle or structures. So that one is bottom to up, from down to up, and this one from top down, top down. You started with bigger size and ends up with the small size particle. So in the top down, usually we use the bulk material. We use the bulk material. Bulk material may be sometime it is few centimeter also, sometime few millimeter also. So bulk material usually bigger, then we convert that big material into powder. Maybe you crush it, you give some kind of mechanical force, or you grind it, or you use certain kind of treatment so that this bigger particle can become smaller. So it can be converted into particle. Again, particle can be crushed or use certain kind of treatment. That treatment might convert this powder size particle into small nanoparticle. So here, once nanoparticle, then also it is possible to create quantum dot like or cluster like structure. Again, give certain kind of treatment to them so that size can be reduced. So this is scale down, okay? Scale down means bigger size, smaller size. And this another approach that we were talking about is starting from bottom and goes up. So this approach of creating nanoparticle is started with the larger size, convert into small size. Mostly they are physical method, mostly. And large scale production is available because you started with the bigger particle. Deposition over large area and large. These are two different things, okay? Large scale production and deposition over large substrate. You can deposit on bigger scale at a time, and large production is also available. In short time, you can create many nano structures. Chemical purification is not required. If the process is physical process, then most of the process don't require any kind of purification because it don't have any kind of impurity. But if the method is chemical, there might be chance that it might have certain kind of impurity. And this method is not cheap because instrument is little bit expensive. Broad size distribution, so sometimes size variation might occur. You cannot get the uniform size. So varied particle is the same thing. Control of deposition. You cannot control the deposition properly because these kind of methods can be conducted in certain environment. Require more time for preparation in some physical methods. And bottom up, started from small and you can end up with the nanoparticle. So here you start from the very tiny small particle and ends with the bigger particle on nanoscale. So this process, I think connection is okay. Yeah. The bottom up approach process start with the smaller and ends with the nanoparticle. It's a combination of atom and molecule to make the complex structure. So it starts with the atomic level, okay? Atom to atom react together, make a molecule and create the nanostructures. It include both physical as well as chemical. Sometimes one method has physics and chemistry also. So physical and chemical methods are included in the bottom-up approach. Ultrafine nanoparticle is possible because reactions start from atom to atom. So possibility of getting the clean, clear structure, crystalline structure is very high. Controlled deposition is possible, comparatively less expensive, because this kind of technique don't need sophisticated equipment, so you can create the nanoparticle easily with low cost materials. Large scale production is difficult because these methods mostly include in the small area, so large production is difficult to create. Chemical purification is required, since atom to atom react with each other and make a molecule and nanostructure, so there might be possibility of byproduct or impurity. So you need to clean the product, you need to clean the nanostructure after deposition. So this is the disadvantage and these are the advantages. Vice versa, like you start with the bigger, create the nanoparticle, and from small structure you can still create the nanostructure. So bottom you start with very small and top you start with the very big. So this, what kind of shape and size usually you get from top down and bottom up technique? Mostly thin film heterostructures, wire rod and quantum dot from top down. You started with the big and ends up, their size and shape is like this. In bottom, nanocrystal, molecular wires, protein, molecule, atom, this kind of possibility of various structures can be created using the bottom up technique. So their size, how about their size? Because we start with millimeter, in some cases centimeter also, and end up with micro or nano also. And here we started with atomic level, okay, atomic, chemical to chemical react on atomic scale. So you start with, atom is in Armstrong, okay, so it start from Armstrong level, and you can see quantum dot or certain kind of molecular structures, molecular wire less than 1 nanometer is possible. So synthesis methods, what kind of methods that comes under the category of top down and bottom up? There are various, but today I will talk mostly about the 8 technique that can be used to create the nanostructures. In top down, ball milling is one of the popular methods. Second is thermal evaporation. Third is laser ablation. Fourth is sputtering. So these are mostly the physical methods, and it is called as a top down method. In case of bottom up, chemical vapor deposition, hydrothermal, co-precipitation, and sol gel. So chemical vapor deposition is a bottom up technique. Hydrothermal is also bottom up, and co-precipitation, like chemical methods. You took certain kind of chemical, mix it, use the reaction is occur at certain temperature, that is called as co-precipitation. And another is making sol and gel and mix them together, that is sol gel method. Those who are doing the research on synthesis of nanostructures, you might work on one of the technique, or there are other methods like electrochemical method is there, electrodeposition method is there, and there are other several methods you are using to create those nanoparticles. So first method is ball milling. ball, okay, a certain kind of ball, milling, like, you know, mixing something in certain spherical shape, that is ball milling movement, okay. So here if you look at the pictures, this picture shows how the nanostructure is created. You have certain kind of bulk material, okay, bulk material, and this is the viol, okay, a certain kind of spherical chamber. In that spherical chamber you are putting the bulk structure, and these red colors are the ball, okay. So this is the bulk material and these are the ball, and now you rotate that. So what happened? Collision occurs. So this bigger ball hit and this bulk particle crush in between, and this process happen very fast. You can increase the RPM. Once you increase the RPM, this ball collision occurs frequently, and when the collision occurs frequently, this bulk material crushed and their size reduce. Their size is reduced, and finally you can get a certain kind of material. So those material is nanostructure. So basically here when you move this ball, so ball crush or grind the bulk structure, and when ball is moving, that movement of anything, if you are standing there is no energy, but when you move you have certain energy. Similarly, when ball is not moving, it don't have any energy, but as soon as you started to rotate this wheel, particle gets certain kind of energy, that is kinetic energy, and that kinetic energy reduce these bulk material into nanoparticle. Of course you can also use the ball milling at high temperature, and temperature might affect the synthesis of nanostructures. So at high temperature the ball interaction and vessel wall, this vessel wall impact severe phase transformation. If the temperature is high, maybe temperature is high means inside this chamber there will be temperature, and when temperature is there, the gas molecule also, you know, quickly goes here and there. So collision happen faster. So ball milling means it is crushing or grinding the bulk material, and this crushing and grinding can reduce the size. However, as I told you that when you crush something randomly, this is not uniform. The probability of hitting this red ball, let's say these two red ball hit sometime this one time, this may be 10 times. So if any red ball hit this blue particle 10 times, it will reduce the size. But if this same color blue has been hit by 5 times, 6 times, its shape will not change as hit by 10 times. So there might be variation in the particle size, because this we cannot control. It is in closed chamber. So this methods is used to create the nanostructures. This method mostly used for metal alloy. This ball is metal ball also, and bulk particle mostly for metal alloy. This kind of method called as ball milling is used. You can see YAG yttrium, garnet, this kind of phosphorus material, the shape is 50 nanometer, okay. But you can see this is 50 nanometer, okay, 50 nanometer. So some particle is very small, okay, like this particle is very small, but some particle is very big, okay. This is very small, this one is very small, this is medium size, and this is bigger size. Why there are variation of size? Because of probability of hitting that steel ball to the bulk particle. So what are the various factors that change the formation of nanostructure? Size of ball, size of viol, like chamber, and what kind of ball we are using, smaller, bigger, or mixed kind of ball. Some balls are bigger, some are medium, and some are small. So what kind of size we use? Then total number of ball, how many balls you are using, the probability of hitting increase if you are using more ball. Speed, rotation, RPM, that viol, chamber is moving at what kind of speed, what is the RPM. Amount of powder, bulk material, how much bulk material you took. If the ball is more and material is less, you will get more fine nanostructure. Ball is less, material is high, you will not get the smaller structure. Milling environment, whether you are increasing temperature or doing the reaction at room temperature. And how long? Time. How much time? Whether you are doing this process for 5 minutes, 10 minutes, 30 minutes, or 1 hour. So that can also affect the synthesis. Number of ball, I already explained. If you increase the ball, the probability of hitting the bulk material become high. The collision, number of collision is also increases, and smaller quantity of powder into the air can quickly reduce into the smaller size, and you can get higher efficiency. So advantages of this method is high capacity, long-term maintenance, simplicity in serving, reliability and safety. So simple method, you have just closed chamber, you rotate the chamber, put the ball inside, and you don't need any kind of other equipment. So method is simple, don't need big equipment, a simple equipment is enough, used to reduce the thickness of stacked material. So sometimes if your intention is to only reduce the size, then this is one of the good technique. If your interest, like you are getting maybe 1 micron size or 500 micron size nanoparticle, you want to reduce the size, then you can put it here and size will automatically reduce after certain time. Disadvantages, the ball mill usually destroy the crystal structure and introduce many defects, heavy and inconvenient. Yesterday I told you that each material has certain crystal structure. Atoms are arranged orderly, that is crystalline structure. But when this ball hit, it has kinetic energy. So when you use your mechanical energy to rub the pencil, you create graphene also. Similarly here, that ball, when it hit, it is possibility that the bulk material might be break at certain maybe atomic scale. Some atom might be gone in the regular arrangement and defect might create it. So chances of creating defect is very high. Grinding consumes lots of energy because of friction, material heating and wear. So when collision occurs, it hit the viol and chances of friction is there, Also, when something is heat, the temperature is automatically become high. Noisy and contamination. If you look at this, it make too much noise because steel ball are there and steel chamber is there. It make lots of noise. It's make lots of noise, and it is heavy and inconvenient also. So it has disadvantages and advantages. Thermal evaporation is very simple technique. The next technique is thermal evaporation. A very simple technique. Thermal. What is thermal? Heat. Evaporation, something evaporate. From one state to another state, it is evaporation. Like if you boil the water, water is converted into gaseous phase. That is evaporation of water. So evaporation of material using certain kind of thermal process. Thermal means heating, annealing, increase the temperature. So increase the temperature to evaporate the material. So what we do in this technique, basically you have certain kind of target material. Any material you put, metal or sometime even alloy, you just put it here in the boat, okay, or crucible. So this one is sometimes ceramic, and this one is the target material. So for example, you put aluminum or gold or silver here, and this is the crucible. This thermal evaporation occurs at high vacuum, okay, inside the chamber having the high vacuum. As soon as you heat this crucible, thermal means heating, you heat this material, that is your target material, the vapor started to come out from your target material, and then they goes in upward direction. They goes in upward direction. Where you have put substrate, it may be silicon, it may be steel, it may be glass substrate. So any substrate you put it here. And then when the evaporation started, this small particle can attach, can adhere, can connect to this substrate. And in this way, you can create thin film. You can create thin film. So this is same principle when you see the boiling of water. But this process is performed in the water, in the vacuum. Thermal evaporation create this thin film. Of course, if you want to have better nanocrystal structures or thin film, you can heat this substrate also. Because when you are heating here, it has certain temperature. Certain temperature means if the melting temperature of any target material is 800, so you need 800 degree Celsius here. But distance between this and this, it may be 5 centimeter, it may be 10 centimeter. So if it is 800 here, it will be not 800 here. So if you want to maintain certain temperature, you need additional heater here, so that these particle can attach to the substrate. If you don't give the heat to the substrate, then this particle cannot attach easily. In some cases like aluminum or some other metal, it can easily, but the adhesion is not strong. If the substrate temperature is there 100, 200, 300, then adhesion become more strong. To keep the difference between this target material temperature and substrate should be minimum. It should not be high, like 800 and room temperature. So since it is a uniform, okay, this evaporation is uniform, they goes smoothly from this target to the substrate, and you can get a continuous deposition of thin film. The process can be affected by various parameters such as temperature, time, how much temperature you are giving to substrate, or how much temperature you are using. For example, I told you target can melt at 8. So how much you are using, 800 or 850 or 900? And distance from source to substrate. So this one target to substrate. How much distance? Whether it is 1 centimeter, 2, 5, 10. So that also decide the quality. Okay, adhesion and thickness. It affects the thickness. If substrate is very near, thin film will be more thicker. These are some of the pictures, ACM images rather than picture, ACM images of bismuth sulfide thin film on ITO. So this is various maybe condition they have put, and you can see the uniform homogeneous thin film can be deposited on ITO glass, indium tin oxide. So we already discussed about the factors those can affect. What are the advantages? So advantages, not require any solvent. You just put the target material into the crucible, give the heat, and evaporation started. So you don't need additional solvent. Suitable for material with low melting point. For example, aluminum. Okay, if you want to deposit aluminum, it has low temperature as compared to other noble metal. So you can get the deposition in quick time. Low cost method among PVD, physical vapor deposition. This is physical vapor deposition. So this is low cost. Why? It need vacuum chamber and heater. Okay, only two things it need. So relatively cheap, relatively cheap. Disadvantages, alloy and metal combination are difficult to deposit. Why? Because if you want to deposit silver and gold, so you put silver and gold, because their melting point is different. It is not possible that they mix up and they will go. It is not going to happen. So that is the disadvantages, that at a time you cannot make alloy, nanostructure alloy, or some metal combination because of different melting point. Only process parameter, control to field, and quality. So process parameter is sometimes difficult to control the quality of the film. Source material could be poor. Sometimes, even though we say melting point of certain material is low and we give the heat, it cannot show the good performance. Evaporation cannot happen as we expected. So that is the material's property. So sometimes deposition is not good. Even the target material has crossed the melting point temperature. Next technique is laser ablation. Laser ablation is the technique that I am also working on. From last 10 years, I am using this technique to create the nanostructure. This technique is physical technique. Although it use liquid, okay? Although it use liquid. In the last technique, we have seen you have target material and you give the heat. That is thermal. Here we use laser. We use laser. So this laser is irradiated on the target material. on the target material. So laser ablation uses this laser, pulse laser, okay, and that pulse laser is irradiated, or it goes toward the target material with the help of lens and mirror. So laser has only one direction. If you want to change the direction, you need mirror and lens, okay? Mirror to change the beam direction and lens to control the diameter of laser, okay? So mirror is required to change the direction. If you don't have mirror, laser is a monochromator source, so it will move into one direction. Then this laser is change the direction using the mirror and then focus onto the target material. We can use various target material like metal or ceramic also, or even polymer. What happened during this technique is very interesting. This is top down technique. Look at this target material, very big, and laser is coming on the surface of this target material. So what happened so that this nano structure is created? So nanostructure is created. Similar kind of incidents happen in thermal evaporation. In thermal evaporation, the particle started to evaporate from the target material, okay, in the vacuum medium. Here, liquid medium. And once laser hit the target material, nanoparticle is created. How? You can see here. Laser energy is used to remove the material from target. This is target material, okay, and bulk material, maybe 1 centimeter by 1 centimeter or 2 centimeter by 2 centimeter. Thickness may be 0.5 millimeter or 1 millimeter. The high power laser pulse hit the surface of target, leading to melting, evaporation, ionization of material. When laser hit the substrate, the possibility of melting target material, evaporation or ionization of material can occur. Why melting? Because if the bulk material has low melting point, the plasma is created here, okay? The heat, a certain kind of heat is created. That heat, if that heat is more, then melting might occur. If heat is not more than the melting point, then evaporation will occur. So evaporation means particles started to get away from the surface, or sometime ionization might occur because of plasma. This is solid material. Target is solid material. Outside is a liquid. So liquid solid interaction or interface is there, and at that interface plasma is created. So due to this plasma, ionization or evaporation can occur. This is pulse laser deposition. Pulse laser. Pulse means 10 nanosecond pulse. Every 10 nanosecond one pulse is going on. So that phenomena occurs in 10 nanosecond. Okay. So this plasma is created in 10 vanish. 10 nanosecond created, vanish. But this is continuous process. Okay. Continuous process. So this heat create shock wave. Like if there is a river and you throw the stone. When you throw the stone, such kind of circular waves are created. Same pattern you can observe in the laser ablation. When this laser is continuously heat and this heat removes some kind of particle, this area is affected, and since this area is affected with the laser energy, the shock wave is created. The bigger the area, bigger the shock wave. This is nanosecond laser. Okay. Nanosecond, why it is called as nanosecond? Because it has nanosecond pulse. This is continuous laser. Okay. When I am starting, this is continuous laser with less energy, so my hand is not affecting. But we are using nanosecond laser with certain energy, let's say 60 millijoule or 60 milliwatt, 600 milliwatt. So here the laser, 10 nanosecond laser like this, every 10 nanosecond one pulse is going or created or irradiated to the substrate. Yes. Okay, okay. This one. Laser is a monochromator source, okay? So when I put, it cannot change the direction itself. I want to put this laser towards you, I cannot. But if I put the mirror, so mirror reflect, okay? It has a concave mirror and that can move the direction of laser. Yeah, possible, possible. But I don't have the picture. Usually laser equipment is like this, okay? And it is big, okay? You cannot put the big laser like this, okay? So laser equipment sometime like this, okay? And we are putting on the table. And we put this beaker somewhere here. So laser is created like this way. And now we want to move this laser here because beaker is here. So that is one of the. If laser is very small, then we can put like this. Our aim is to put the laser vertical, okay? Another way of creating the nanostructure is you put laser like this, okay? Simply like this. There are two ways you can create the nanostructure. One way, you use target material in the form of solid. Another, you just simply put the powder. The powder size is few micrometer, let's say 1 micrometer or 10 micrometer. So you just mix the powder, and you can also use the stirring. And in that case, you just put this laser horizontally, okay? This laser is vertically, okay? We are putting vertically. Another way, you just simply put your beaker here, that's it. So like this, you can put, it will be created, okay? So there are two ways. One is irradiate with horizontal direction like this. Another is change the direction of laser and make it vertical. So if the laser is nanosecond, more heat affected area. But if laser is femtosecond, imagine, okay, nano and femto. Nano means 10 to the power 9. Femto is more small, okay. So femto affect less area and less shock wave. So this is the difference. This is the difference. If the area is very small, then you can get more smaller particle. So basically what we do, earlier was, this is vertical laser ablation, vertical. Another is horizontal, like this, okay. We are just took the water, and in that water we put the powder, any powder, you whatever you want. For example, SNO2, WS2, even RGO, any powder, you just put it, close the glass beaker with the lid, and then use this laser horizontal. Of course, you use here magnetic stirrer so that powder should disperse uniformly. And after certain time, you can get the nanostructure. After certain time, maybe in some cases it is 5 minutes, in some cases it may be 10 minutes, 15, or even 20 or 2 hours. We are using 532 nanometer wavelength, okay, green. This is green, okay. Such kind of laser we use. This is the example, indium selenide. Indium selenide bulk powder we put into the water, and this is the specification of laser, Nd:YAG laser with 500 nanometer and 620 milliwatt power. After 5 minutes, this bulk material, so bulk material means it has a size up to 1 micron, 2 micron, or even 3 micron. That bulk material is in the form of sheet, okay, like paper. When you deposit this for 5 minutes or irradiate laser with 5 minutes, it started to change its shape into the rod-like shape, and there are some spherical particles. After 10 minutes, rod again vanishes, it becomes spherical and few rods. After 15 minutes, the rod started to convert into the cube, and after 20 minutes, the uneven shape cube become even shape nanocube. Within 20 minutes, you can get the formation of nanocube. So this was the paper published in 2021. This way you can see how the size reduce, You started with the bulk material. Earlier was ACM image, this is TM. This one is the bulk material you put here, okay? And this is sheet, like paper sheet, one by one, top, like that. But this sheet, 2-dimensional, is convert into 3-dimensional nanocube. So these sheet align themselves and change their shape into cube. Yesterday I told you, if you have high surface area, the more reactive area is available for reaction. So here more area is available, and since more area is available, it can be used for a certain kind of application. In our case, we have used it for field emission application and photocatalysis also. We characterize this material and see whether indium selenide was indium selenide or not. So here is bulk material, then this is the nano cube, and structure is intact after TM and XPS. Next experiment we done, we took powder, this time horizontal laser ablation powder, uneven powder. We crush it, okay, for 2 hours and make it fine powder, put into the water and do the laser ablation for 2 hours, and you can see black color powder change into yellow color. Yesterday in my first lecture I show you gold bulk is yellow color, but you can see different kind of color for the gold. Same thing is happening here. If you see the bismuth selenide powder, bulk powder, it is black color, but after 2 hours it become yellow. So when it become yellow, it will show different property, definitely band gap changes, conductivity effect. So bismuth sulfide is also kind of topological insulator, but it convert into semiconductor, and this material can be used for FET application. So this is the after crushing, okay, after crushing, these are sheet like structures, then it convert into rod, convert into nanocube, convert into rod also. So there are 2 ways this growth mechanism occurs. One way, when you have large bulk particle, when laser is irradiated on this bulk particle, this sheet like structure breaks into several small pieces, okay, small pieces, again laser collide again into small pieces, cluster like formation and then creation of nanopart. This is one of the possibility of formation of nanostructure, like you can get small spherical nanostructure. Another is this bulk cannot crush or divided into small particle, but it like having small sheet after laser striking. It convert into small sheet. Only few area is affected. This time only half. Another laser pulse come, then again this area is break and it fragmented. Like if you have paper, you make it in several pieces. You make it half, then again quarter, and then 8 pieces. So same thing can be happen as laser irradiate on this sheet, and you can get sheet-like structure. So when you have sheet-like structure, it can align itself, and certain kind of shape can be possible to transform the two-dimensional nanostructure into rods, into nanocube, or into different kind of structures. So this laser ablation can be controlled on various parameter. When you change this parameter, fluence, wavelength, repetition rate, pulse duration, transmission or light absorption, how much energy, how much time, how much fluence, what kind of laser you are using, those all parameter can control the synthesis. Even the chemical composition of liquid can affect the laser ablation. In our case, we are using water. Sometimes we use methanol, ethanol, or combination of water and ethanol, 30% ethanol, 70% water. Sometimes we put the bulk material into water, but it cannot disperse. If it cannot disperse, then we need to use a certain organic solvent like ethanol or methanol. Then it can disperse and uniform formation of nanostructure is possible. Since this synthesis carried out in pure environment, in liquid environment, pure nanoparticle can be formed, low loss of energy. All energy is utilized because energy is given in the form of pulse. Less waste and eco-friendly. So byproduct is not created. That's why no wastage of material, and it is relatively low cost method except the price of laser. There are some disadvantages. Lots of energy we use because to on the laser you need high power supply, unable to produce nanoparticle on industrial scale. Since this pulse is very small, it cannot create the large area deposition. Efficiency of ablation decreases with longer ablation time. If you put the laser for longer time, the efficiency decrease. Like I have shown you indium selenide. After 5 minutes, rod. 10 minutes, rod plus spherical. 15 minutes, uneven cube. 20 minutes, cube. But if you go after 20 minutes, that cube started to again convert into ball. Okay? So longer laser time is not good for some structures. The fourth one is sputtering. Sputtering is also popular technique to create the nanostructure. In this case, it is very similar to thermal evaporation. But here also you use the target material. In thermal, you literally give heat to the substrate. Here, RF sputtering or magnetic sputtering. Those source of energy is RF sputtering here instead of thermal heating. Then RF sputtering heat the target material, and again similar kind of phenomenon occurs, and after evaporation you can get the thin film on the substrate. Because when RF sputtering is used, high energy ion is created. Thermal energy cannot create the ion, but this sputtering create the ion and it strike on the substrate. Once this substrate is strike with the high energy ion, they try to goes toward the substrate, and in this way thin film can be deposited. It require various kind of RF source to activate this target element or target material, and this process is created into the vacuum condition. Once we use this RF sputtering, it has use in the vacuum, and electric potential must be applied between two electrodes. Now, if you look at this, in thermal evaporation you simply heat, but here RF sputtering. So electrode is used like positive, negative, and due to RF this sputtering, the electric charge, electric field is between this anode and cathode. So that created ion is attracted toward the substrate or move this particle toward the substrate. Now, this evaporation is in gaseous form because of vacuum. So this particle move toward the substrate. And in laser ablation, plasma is created. Here also plasma is created. Why plasma is created? Because you apply electric field between anode and cathode. That's why charge particle is created. So once charge particle is created, they attract towards, so this is cathode, this is anode. So oppositely charged particle attract to each other. Sputtering can give you uniform deposition. Also, sputtering is used for low nanometer scale. Like if you want 1 nanometer coating, then sputtering is very good. 2 nanometer coating of certain material like AG, AU, you can use sputtering. And uniform deposition. Look at this, okay? These are the example like AG, okay? 1 nanometer, okay? 6 nanometer, 8 nanometer. So 1 nanometer is uniformly deposit. These are the factors which affect the synthesis: temperature, time, and layer of thickness that affect the deposition. Target to substrate angle, bombarding particle mass and energy, air argon ions in vacuum. Substrate temperature. So when you apply electric field, substrate need to be heated so that uniform deposition can occur. These are the advantages. It can work at low temperature. Like in thermal evaporation, high temperature is required. High temperature means melting point, then and then substrate will evaporate. Here low temperature is okay because plasma is created due to the electric field. Large area deposition with uniformity. You can put large silicon sample like 6-inch vapor you can put, and it is possible to create the large area deposition. Elements, alloy, compounds can be deposited. So in thermal evaporation we cannot create alloy nanostructures. Disadvantages: deposition rate is very low. So Sometimes 1 hour deposition only few nanometer. So this is like time consuming process. However, uniform. Target convert most of the energy into heat. You are applying electric field. So most of the energy is given to the target material, expensive equipment and need more time. We have 20 minutes and I will try to cover 4 techniques, but this technique, one of the technique is very important, chemical vapor deposition for bottom up. I will skip this slide. Chemical vapor deposition. Chemical vapor deposition. Chemical means use chemical. Vapor means vapor are created. Deposition means deposit the substrate. So this is the simple meaning. In this case, you took 2 gases. One gas is precursor, another is non-reactive gases like argon gas. Sometimes you can use reactive gases also. Here what happened, there are heater and this is gas in and gas out in the vacuum. So this CVD technique use gases. It is bottom up. I told you that in bottom up the reaction started at atomic scale. Okay, so when you are using the gas, now gas molecule. In the gas, what is gas? Gas means gas molecule and they can move here and there. So matter of state, liquid, solid, gas, plasma. So in case of gas, these gas molecule are free molecule. They are not attached to each other. So this gas molecule come here and they get heat, and when they get the heat, they break into the spaces, and these spaces, reactive spaces, only deposit on the substrate. Remaining spaces can come out through these gases out. So I will explain this, how the nucleation happens in CVD technique. What happened? Basically, nucleation and growth is very important. I just show you that how indium selenide nanocube is formed by laser ablation. Similarly, how nanostructure is formed. Whether it is liquid or gas, initially there should be some kind of nucleation. Like if you want to have the building, you need foundation. Then you can build the big structure. Similarly, to create the nanostructure, you need some kind of nucleation, some site that can grow the nanoparticle, some base. So that is nucleation. And then that nucleation start the growth of nanostructure. How it happen? In case of CVD, let's see. When you put the gas, okay, this is argon gas and this is, let's say, hydrogen gas or methane gas. If you put this methane gas, methane means CH4. Now C means carbon, H means hydrogen. So this carbon and hydrogen species will come into the chamber. Now chamber has certain temperature, high temperature. This high temperature will break CH4 into carbon and hydrogen. Your target is to deposit carbon. Then you don't need hydrogen. But this hydrogen you don't want. The argon gas will push this hydrogen molecule to the gases out or exit. Okay. Remaining C, that is carbon, will push toward the substrate. So this way, initially what happened, the species can break due to the temperature, and like MCl2, and H2 means that non-reactive or reactive gas. Argon you can take also. When this carbon and hydrogen species is decompose, separated, break down, only reactive species attract or goes toward the heater which has a substrate holder, and carbon can be deposited here. Remaining particle can goes out. When you heat this chamber, this, let's say, green and yellow molecule means it has two atoms, and you push some kind of hydrogen or argon also to transport this molecule, to push, and after a certain time this movement continue, one certain amount of gas come, and then again you have heat, and this argon or hydrogen is transporting these species toward the substrate, okay, like this. Now uneven or unwanted or impurity or byproduct gas will come out from the exit, like CH2 means carbon and hydrogen, and if you use another hydrogen gas, so that C will break and H4 will break, but that H4 will react with hydrogen, and when this, here is CH4, okay, CH4, and this is hydrogen. Now this hydrogen will react with this hydrogen like this, and then this will react, and then it will throw outside the chamber. Only C will remain on the substrate. So this way there are many processes, but due to time I am not going to explain you. Only remember that in CVD methods breaking of material happen. So any material, any gases, usually it is in the form of carbon and hydrogen, and that carbon hydrogen species break due to the temperature. Remaining unwanted hydrogen like species react with argon or maybe hydrogen, and they can throw out from the chamber. So these are some of the chemical reaction occurs in the CVD method, like pyrolysis, like separation of species, oxidation, sometimes hydrogen to hydrogen react, sometimes hydrogen react with sulfur also, and H2O gas can release, sometimes chlorine gas can release, depending on what kind of gas you use. And these are some of the example of nanostructures. What kind of factors that affect the deposition, like pressure, gas flow, time, precursors of nature, what kind of gas you are using, and temperature. Large area fabrication is possible, uniform coating can be done, homogeneous structure can be obtained, growth rate can easily regulated. We can control the growth rate because when we use the CVD, we know the growth rate. After 1 hour, 5 nanometer happen. After 2 hours, certain nanometer can be seen. So we can control the growth of nanostructure, and it has reasonable processing cost. It's not like high cost technique. Only gases is expensive, other thing is not so much expensive. It do have some kind of disadvantage, like gases sometimes explosive, like H2 gas is reactive, highly explosive gas, or sometimes silane is also used to create amorphous silicon, and it has some limitation like high temperature, sometimes poisonous gases can create the hazardous gases like chlorine or even sulfur. Hydrothermal is a pure chemical methods. In hydrothermal, what you do, basically you took two solution, you mix it together, two different kind of chemical, you mix it and put into the autoclave at certain temperature. So here you have precursor solution. Precursor solution means you have A solution, B solution, you mix it together and then transfer into the autoclave. Autoclave means steel chamber, okay? Steel chamber, and it is closed chamber. Then you put this chamber for at certain temperature, let's say 180 or 200 degree, and after certain time, after certain time nanostructure can be created. Then this nanostructure is in liquid form. You can remove the water content and get the powder. You can dry this solution and get the powder. That is hydrothermal. This is very simple technique. You just need one steel small chamber. You put into the furnace for heat treatment, wait for certain time, 8 hour, 10 hour, 12 hour, 24 hour, and then you can get the nanostructure with different size and shape. This is very popular technique because of two reasons. One, it is low cost. Another, it is very simple technique. Once you mix two chemical, put into autoclave, just transform this autoclave to the furnace and done. Of course, after this you have to dry this solution using vacuum drying. And these are some of the structure. You can see how this structure has been got. By the way, these structures are three-dimensional structure. Okay, yesterday we have seen such kind of structure is three-dimensional structure. It can grow in three direction. Okay, so this is three-dimensional structures. These are the parameters that affect the technique. Mostly high temperature pressure, because autoclave is closed environment. Reaction time and solvent. What kind of solvent? Whether it is water, whether it is ethanol, whether it is a mix of ethanol water. What kind of organic solvent you are taking? Advantages: precise control of size of a nanoparticle, low melting point, high vapor pressure, tendency toward the pyrolysis will be obtained. These are the advantage. You can get the nanostructure at very low temperature, like 150, 180, 200. In thermal evaporation, temperature is in 1000. Melting point of, in other technique, even HFCVD or CVD, temperature is very high, or sputtering, temperature is very high. Comparatively, here temperature is very low. Disadvantages: crystal growth information cannot be observed directly. We cannot see what happened. We cannot predict how the flower is generated. We have to guess, we have to use our knowledge and then predict the growth mechanism. Expensive autoclave, it is still difficult to control. Sometimes the formation of nanoparticle is difficult to control if we don't know how this particle is transformed. Co-precipitation is a chemical technique, is a simple chemical technique. What is the difference between hydrothermal and co-precipitation? In case of co-precipitation, you just add two solution and mix it, either stir or just aging, and you can wash the solution and get the nanoparticle. In case of hydrothermal, hydro, water, thermal, heat. There is no thermal. So hydrothermal means water and heat. Precipitation means only mixing and stirring or aging, you can get the nanostructure. These are some of the pictures. These are the parameters that affect the formation of nanostructure. I will not read, we are coming to the close of this talk, so I will not read. You will get the slide. And sol gel is the last method that I want to tell you for a few minutes. Sol gel means sol and gel. Sol means solution. Gel, you know the gel. So here sol and gel is created separately, sol and gel. Sol and gel. Okay. So this, you took certain kind of solution, and with the hydrolysis you can create the solution, and after that it transform into gel, and this gel may be processed for thermal drying or different kind of superficial drying or freeze drying. So high temperature or low temperature. Thermal means high temperature, freeze means low temperature, and then you can create the nanostructures. So basically sol gel means it kind of colloidal solution which form into the liquid having the size up to 100 nanometer. The gel is the solid micromolecule immersed in a solid. So gel is look like solid, but it is called as micromolecular size. And solution means it's pure liquid, pure liquid. So you mix together and give certain kind of pre-treatment to make the nanostructure. These are the pictures. Sol gel method also produce uniform structure. These are the advantages. When you are using the water and you use some kind of pre-treatment, in that case pH is very important parameter, then speed, stirring time, and temperature, time for reaction can affect the structure quality, porosity and other factors. Solvent, precursor are very important parameter. Texture and surface quality of material is controlled very well. Desired nanoparticle with correct crystal size can be obtained. Advantages, it's very simple technique because you create solution and then gel and give the certain kind of post treatment. Uniform, highly pure structure can be created. Low temperature allow introduction of modest amount of dopant into sol that is equally spread into final product. So sol and gel, you can choose how much you can mix them together. Disadvantages, long reaction time. So reaction time sometimes 24 hours or more also. Use organic chemical might cause health risk. Some of the organic like H2O2, okay, peroxide, if you are using for zinc oxide, so that kind of chemical is might be risk for your health. Purification is required to get the nano. So after chemical, any chemical deposition, chances of impurity is very high. You need to clean the nanostructure. So today, with this, I have shown you the synthesis method, 4 method of bottom to down, and another, top to down and bottom to up. So most of the technique that was seen earlier in first part, that was physical technique, and bottom to up was chemical technique. Total 8 technique we have covered, and you might understand now what kind of structure can be created. So what is your desire? What kind of nanostructure you want to deposit? 2-dimensional, 3-dimensional, rod, particle, uniform, 1 nanometer, thin film, coating, liquid form, dried. You can choose any one technique and deposit those material. So with this, I will stop here, and if you have any question, please ask question. Thank you very much. It's almost 12 o'clock. Do you have any question? Yes? Nano scale material too? Nanoscale to picoscale. Yeah, I have told you that when you are going from top to bottom, you need certain kind of treatment, like whether you are grinding, you are crushing, or you are giving certain kind of energy to cut the particle. If you want to go towards the more deeper scale, like picoscale, for example, if you want to use the laser. So laser means what? It remove and cut the material on the surface. So possibility, if your surface is in nano size, and if you put the laser on it, irradiate the laser, it will convert that into pico also. Okay, but to convert into the pico, you need very fine laser. Very fine laser. Diameter should be very fine, like less than maybe 0.1 micrometer, so that reaction should occurs in small area. If the beam is very big, it will affect large area. So small particle will not generate it. In case of nano, large plasma is created. In case of femto, small area is. So femto, the size is 5 nanometer. If you want to go more deeper, you need another octo laser, because one of the technique, or if you process it like grinding, ball milling is also one of the technique. You need to give certain kind of treatment. It may be crushing or something to reduce the size. Okay. Okay, please. Means you are talking about the vacuum, right? So in the vacuum, when you have heat, so when you have heat, particle always move up. They don't have gravity because it is vacuum. Okay? In the vacuum, usually particle lay down. If you want to activate them, you need to give the energy. Then that particle will go into the upward direction. Yeah, without they are gravity free, not gravity free. You cannot push, like if the particle is here in the room temperature, they will not go themselves up. You need to give some kind of energy to push. Okay, otherwise they will just stay on the surface. Air, yeah, if they are light gas molecule, okay, they will be, if their densities, they will be in the air. Okay, so like fog. Okay, why fog is? Because their densities, so they are just laying here, and when they become bigger, so they come down. Any other question? If no question, then maybe we can take a break for, I think, half hour. 20 minutes. Okay, okay, 20 minutes. 11:25. Okay, okay, okay. Thank you.
Hello? Can you hear me? Okay, good. Okay, thank you so much. Here's my personal introduction. Already the chair introduced about me. So I was actually got the PhD degree in Japan, and after that I joined the USA in Monterey, San Francisco. So now I am working as a full-time professor at the National Korea Maritime and Ocean University. I will retire after 1.5 years later. But just in case, my retirement will be extended 5 more years as a chair professor. I established several conferences, international conferences. Among them, I established one international conference related with engineering education, Asian Engineering Education, okay? ACE 2009. So we enjoyed this conference. So I organized several conferences. Actually, I was president of this KSCM, Korean Society for Composite Materials, until 2024, the end of December. So this KSCM was founded in 1987 as a scientific engineering and professional organization. It has more than 5,000 members, 5,000 members. I also organized this kind of international conference, ACCM 13, every 2 years. Last year was held in Kyoto, Japan. At that time, more than 300 participants were there. So at that time, I made a plenary speech there. Can you find me here? Here. I was here. Yeah. And this is steering committee members from Australia and Japan and Hong Kong and China and Korea. This is a steering committee member from South Korea. This is also, I am organizing in Vietnam, MMMS. Okay. This is from Japan, AMDP, Advanced Material Development and Performance Conference, every 3 years. From now, I'd like to introduce our university briefly, located in southeastern tip of Korean Peninsula. Busan is the second largest city in Korea. It will take us 3 minutes, just like. our university is established firstly as a national university in Korea. Actually, it was established in 1919. And from now, I'd like to introduce about our composite lab. Here, me, and I have two postdocs from India. Right now, from Sanjay Kumar, he's very smart, and he has really good ability to publish many papers. And I have also doctoral candidates from China and also Kenya and Pakistan and from Korea. And also I am collaborating with several institutes in Korea. They are all my ex-students. So let's enjoy. I'd like to introduce about my ongoing research. This is closely related with Korean air. So I'd like to introduce briefly. This is included some kind of a secret factor because it is closely related with industry. Please to remind ongoing research. Here, this is my first project from our government. Development of a partial structure for the entrance wall based on thermoplastic composite materials in a single passage class aircraft. I am now collaborating with Korean Air and Airbus and so many institutes like this. Korean Air and Songwall Technology and ANH Structure and KITEC, several institutes were included in this project, consortium project. As you know, our composite material is widely used in aircraft and automotive and ocean industry, shipbuilding. So very important nowadays, especially in aircraft is used more than 50%. So our final target will be like this. Every day we evaluate and we apply. Like a stiffener and skin by using the oven consolidation system. Like this, and the skin, stiffener consolidation system. And the second one, the development of a skin spar integrated wingtip. Yeah, this project was done during 5 years. So all those results from 5 years research. Here's our background. And manufacturing process is like this. And AFP and the high temperature RTM process, resin pressure molding system we are using. And our final end product will be like this, wingtip full scale. And another one is aircraft structure based on thermoplastic carbon composite. So as you can see here, my project is closely related with mechanical engineering and material science and nanomaterials. So you can see all those fields. Our background is like this. We are now trying to develop this kind of cargo door. And our end product will be like this. The procedure will be like this. And also the fourth one is development of technology for integration of 2.0 5-meter class cargo door, very similar one, and the product will be like this. And the final one is development of a skin spark also, final and the product. And the procedure will be like this. So we are trying to develop that kind of structure and end product. So to achieve that kind of structure, my research focus are like this. The first, FRP composite with the thermal setting resin. We use this kind of fabrication method during 10 years. Infusion molding and vacuum assisted resin transfer molding and handlay process out of autoclave. This is a recent trend. And the fiber spinning process and the filament winding, resin film infusion for this kind of thermoplastic resin. And also thermoplastic resin. This is also trend. Stamp forming, oven consolidation, and hot bread. As a processing and the testing method, optimization of process parameters and the environment degradation, the functional characteristics. Today my research flow or presentation flow is like this. This is a systematic research for 5 years research. First, combine the effect of open hole shape pack compartment. When we create hole, the stress concentration will occur. So how can we treat that kind of okay? So effect of geometry, also temperature on tensile property, pinned joint of shape pack compartment. And the fourth one is bolted joint. The fifth one is left shear properties of a shape pack composite with a nanoparticle enhanced adhesive joint. And sixth, effect of melt infusion of PT, PI, and P, thermoplastic film. Interleave on the flex toughness and failure behavior of carbon fiber composite. The seventh, optimization of interleaved structure with amorphous heterosect nanotube for superior performance of CFRP. The seventh, optimization of interleaved structure with amorphous shared pipe for shipping. Finally, I will conclude this systematic research. Okay? Here is my research flow chart. First, we have to know the basic mechanical property. So it is the first one. And open hole properties are crucial for composite structure. because open holes are often required for joining application. And pin joint properties are essential for the joining of a composite structure. Voltage joint properties is also very important for composite structure. And adhesive joint properties are essential for the joining of a composite structure. As you may know, the composite material is very serious problem due to the delamination problem. So here, basic properties are necessary to restrict the delamination that occurs at open hole joint, pin joint, and voltage joint. Also, we have to apply this kind of composite structure to industry, like the aerospace and automotive and shipping. So, industrial purpose composite structure very important to develop. So, I'd like to present the first issue topic. Combined effect of temperature and preventing on the fracture properties of carbon fiber polyethylene composites. So from now, let's enjoy. Okay? It's not this year. As you can see here, fiber reinforced thermoplastic polymer, FRTP, is widely used in this aircraft, and also UAM structure, also automotive. We are now targeting to apply in this structure. So the classification of plastics is like this. Amorphous structure as a super engineering plastic. This and engineering plastics is like this. And also as a semi-crystalline here. I'm now using this kind of pack, shell pack. So just to remind this. In aviation, the cruising altitude will be 9 to 12 kilometers, right? And the temperature is minus 40 to minus 7. So our temperature range will be minus 196 Celsius as a crucial temperature, critical temperature. And also minus 60. And our ship pack is the transition temperature is 159. 159. So we decide the temperature 140 and 200. This is our temperature range for experiment. We prepare the specimens like this. The CF-pack composites are fabricated with 12 layers of pre-prep and consolidated under vacuum and achieve a thickness of 1.7 millimeter and an exceptionally low we have to lay. The procedure is like this. We stack the pre-pack 12 stacked layers CF-pack and by using the vacuum bag and we use the oven consolidation. After that, we prepare the finally composite plate. Shape packs shear strength increases. Shear strength increases, but the shear strength decreases due to the thermal strain and matrix failure. Same images show distinct flexion pattern, indicating more brittle behavior and reduced deformation. Same images show distinct flexion pattern. Is it okay? Okay. And also tensile property and the failure behavior of shape pack at different temperature. Stress strain curve, also the temperature range and the fracture pattern. In case of room temperature, the fracture pattern is like this: low temperature and extreme cryogenic temperature. So this slide means tensile tests show the shape pack, the Young's modulus and the strength increased with decreasing temperature due to reduced polymer chain mobility, enhancing rigidity. At the lower temperatures, improved fiber matrix bonding and reduced ductility, resulted in higher tensile strength and more brittle fracture. This kind of result published in composite part A. The impact pattern is more than 7. A very good journal. So this slide shows the fracture stress and strain relationship. And as you can see here, the temperature decreases. The temperature decreases. Extreme cryogenic temperature decreases. Shape pack composite exhibit increased the fracture strength. More increased and toughness due to the enhanced matrix rigidity. Transitioning from compressive to tensile failure mode, thus improving overall low temperature performance and damage resistance. Just look at this mechanism. Thermal stress will be occurred like this. In case of fiber, under compressive, and matrix under tension. This kind of residual stress will be occurred here. The fracture mode will be changed. This slide shows the effect of prevent on fracture behavior of shape pad. As you can see in this figure, increasing pre-bending leads to reduced fracture properties in shape pack composite, with a significant decline in modulus and strength as prevent approaches and exceeds the material's yield point, causing extensive micro-cracking and debonding. Under 30% prevent and 70% prevent, you can compare. In case of 30%, like this, and in case of 70%, cannot be reverted to the original point. The pattern is very different. We also observe the fracture morphology. Also, effect of temperature on fracture behavior of prevent shape pack you can compare in case of a 30% prevent the fracture or force like this. Just look at the procedure. Temperature and preventing significantly affect fracture properties at the low and extremely low temperature, while modulus changes are minimal. Strength and strain increase, highlighting shape effects resilience, but also revealing increased matrix cracking and reduced post-yield modulus. Just look at the fracture morphology. Can you follow me? Yeah. Let's go slowly. And this slide shows the effect of the temperature on the fracture behavior of prevent shape pack. In case of a 70%, big difference. Low temperature, extreme cryogenic temperature. The micro cracks will be occurred like this. Micro cracks. Low temperature, extreme cryogenic temperature. Micro cracks will be occurred like this. So you can compare between 30% and 70%. This slide shows the residual flexion strength. Room temperature, extreme cryogenic temperature, and low temperature. Residual flexion strength in shear pack decreased with increasing prevent intensity, but 30% prevent specimens retain the highest strength at all temperatures. 30%. Highlighting their durability for demanding aerospace applications. This is a very important result. So under 30% prevent, we can use. This is very important result. So our consortium is using this data. I'd like to move to the second issue. Tensile behavior of open hole and pinned joint and the bolted joint of a shape pack composite under extreme temperature. Mechanical joints offers several advantages, like easy installation, repair, and resistance to environmental factors, and higher safety factor, reliable and preferred joining method in modern composite structure. But when we create a hole, the stress concentration will be occurred like this. It will reduce the life of composite. So you can see this kind of procedure. So at this point, it is very important to check the joint efficiency. The joint efficiency here. Joint strength influenced by joint geometry. Width to hole diameter, W/D ratio is very important here as a parameter. And edge distance to hole diameter, E/D ratio is very important. So in this paper, very important factor is W/D and E/D ratio. So the systematical research will be performed. We use the shape pack prepreg provided by Solvay company. And as a specimen preparation, the procedure is like this, and we use the oven consolidation. We prepared 4 kinds of specimen here. As an experimenter, unnotched tensile specimen based on the ASTM D309. The second, open-hole specimen prepared based on ASTM method, and the pinned joint also based on ASTM method, and the bolted joint based on ASTM method. We prepared 4 kinds of specimen like this: unnotched specimen, and open hole, and pinned joint, and bolted joint. Here we are coping with some limitation, because this is a very, very expensive material. 1 roll, the price will be 10,000 US dollars. Very expensive material. So it is not easy to handle this material. So we have to be careful. We are careful to handle this kind of material. Really, very expensive. So we have to be careful to prepare this kind of specimen. First result, tensile properties and the failure behavior of open hole shape pack at different temperature. Let's look at this data. This is from the reference value. Composite, carbon epoxy, aspiglass epoxy, and carbon epoxy, Just look at the strength retention value, around 45 to 52%. But our shape composite, the strength retention reached to the 69%. This means this is very good, high quality material. So we are using this material. This slide shows the tensile properties and the failure behavior at a different temperature. Also, we published in Composite Part A journal. We changed the W by D ratio 4 to 1.5, 1.5 to 4. So just compare those values, those behavior. In case of 1.5, the behavior is like this: small strength, and 2, 3, 4 at low temperature and high temperature. The fractional morphology is like this, will be changed like this. The failure behavior of pinned joint at the different temperatures. W by D effect under constant E by D ratio equal 4. Just compare the result. We prepared this kind of specimen. The result is like this. In case of W by D equal 1.5, low temperature, room temperature, high temperature. Low temperature and high temperature show the decreased peak load. with different trend in stiffness and displacement, right? Just look at the flex behavior. In case of 1.5, totally occurred net tension hold. In case of 2, can you see the bearing failure mode? Not the net tension. Called bearing error. This is the result, 3 and 4. Whole bearing failure. Bearing. Divided by the 3 and 4. So, finally, we summarize like this. W by the effect under constant A by the ratio equal to 4. Marginal load increased due to the same bearing failure. Increased specimen width prevent the net tension failure move. Bearing failure achieved beyond W by D ratio 1.5. Very important result. Just compare low temperature, high temperature, same double by the ratio. The flex will be occurred like this as a bearing mode. And pin joint shape back at different failure temperature, the flex behavior. Geometry effect at different temperature, E by D ratio effect. Just before we compare the W by D ratio. This is E by D ratio under W by D ratio, the constant ratio. Okay. So increasing E by D ratio shows a slight increase in the peak load. Just compare the peak load under the different temperature range. You can compare also the flex morphology pattern. Very similar. Very similar. Just we'd like to compare the bearing strength. Bearing strength between bearing strength and the W by the ratio. So the right thing. Bearing strength primarily influenced by W by the ratio, right? And E by the ratio had minimal impact. Also, bearing strength at the low temperature and the high temperature slightly lower than room temperature. W by the ratio and D by the ratio equal to 4 shows the highest bearing strength. Right. This is also a very important result as a bearing strength. Let's compare with the reference value. Carbon epoxy. Carbon epoxy, carbon epoxy. The stacking sequence is like this. Movement and the sequence is like this. The bearing strength, the value is like this. Just look at the value. Almost from 160 to 370 range. Right. So here, our shape pad reach 428 megapascal as a bearing strength. Very high level. Just just the people 160 to 370, right? But here, 428 megapascal. So it means not worse level of bearing strength. So we are use this material. Tensile property and failure behavior of pinned joint at different temperature as failure behavior at the room temperature. W by the effect 1.5 net tension. To practice morphology is right there. Just compare. In case of W by equal 2, we observe here the fracture morphology is right here. Buckling and kinking and kink collapse and bending failure and shear shaped crack and shear driven compressive. So we can observe the intralaminar crack and interlaminar crack. We can observe here. Very important result. So complete bearing failure was achieved as the double body ratio increased to 2 and beyond. As the load increases, the matrix undergoes plastic deformation, leading to fiber buckling and increased specimen thickness and eventual failure. Fiber kinking causes the bending failure in the 90-degree lamina, promoting the shear-driven compressive failure. So, just before we compare the result, double by the ratio, from now, E by the ratio, under constant W by the ratio. E by the ratio equals 1.5. Intralaminar crack caused by kinking in 0-degree propagated to the edge, contributing to the lower bearing strength. And the higher E by the ratio than 1.5, intralaminar crack confined to the whole region. Due to large distance between the hole and the edge of the specimen. At the low temperature, we can observe the buckling and the kinking and the kink collapse, bending failure, and the shear-shaped crack, shear-driven compression. So temperature changes, the thermal deformation occur along the 5 directions. Intralaminar crack and interlaminar crack also will be occur. At the low temperature, fiber under compression, matrix under tension. So the reduced thickness of specimen due to the temperature-induced acceleration of a localized compressive failure. At high temperature, we can observe the cracks pattern like this. At high temperature, increase the ductility, right? So increase the ductility of a pack resulted in significant large plastic deformation and external phylum you can observe. In this case, fiber under tension, matrix under matrix, right? So severe bending failure in 90 degree due to the accelerated compressive failure of macro. We check the situation by using the DIC. In case of 1.5, geometry effect, load displacement. DIC means that the 99% failure displacement reveal minor bearing before flexion with predominant nutation failure. We check the situation. In case of 1.5, in case of 2, just compare the fracture pattern. Increasing W by the D to yields 66% higher peak load and displacement. DIC images show increased bearing, the shifting from nutation to combined nutation or bearing mode, with minor bending near the bolt contact area. This is W by D equals 3. DIC pattern like this. I will skip this, very similar with the previous slide. Just look at the fracture pattern, bearing area. Here, the fracture morphology. I'd like to change the temperature effect at the different W by the ratio, 1.5, 2, 3, 4. Just compare the result. Temperature influences the load bolt displacement. Low temperature enhances the stiffness and the reducing displacement. High temperature degrades stiffness and increase the pilot. Finally, we compare the joint efficiency depending on the W by the ratio. Let's look at the result. Because of time limitation, I'd like to move to the next issue. Here, strengthening of a composite through incorporation of a hollow side nanotube. From now, I'd like to move to the nanomaterials effect. This slide shows the left shear properties of shape pack composites through nanoparticle enhanced adhesive joint. We prepared the specimen like this. Schematic illustration of the preparation of PEI, HNT means hollow side nanotube, film for shape pack adhesive joint. We observe HNT dispersion situation. In case of 1% HNT and 3% HNT, we can observe the nanoparticle aggregation. This is a very big problem in cooperating to the composite material, because this kind of aggregation occurs the stress constraint this is a big problem, so we have to solve it. So, in case of this aggregation situation, two stages of aggregation will be occurred. First stage will be occurred by van-der-Waals force, and second, chemical shrinkage. So, two types will be occurred. So, 0.5 and 1.0 and 3%. The situation is like this. We check the thermal properties. Tg will be changed against the PI 3% and 1%, 0.5, and PI need. You can just look at the Tg. Check VS condition and cross transition temperature. Also, we performed the lab shear strength test through nanoparticle enhanced adhesive joint. The lab shear strength for 0.5 HNT is the highest value shown. This is the main result here. Over 0.5 decrease. So we finally used this 0.5 result. Also, we observed the flex pattern, 0.513%. Detection of SI and AL indicates the bonding joint interface is formed by the complex layer of packed PI and HNT. Situation is like this. PI need, PI plus 0.5 halosecond cube, flex morphology. We can observe several phenomena here. In case of PI need shows smooth ductile drawing and exposed fiber and exhibits poor bonding between fiber and resin. 0.5 is the most important for the person. So 0.5 shows rougher ductile drawing with resin residual and cushion morphology, indicates the improved interfacial bonding. In case of 1 and 3, just to look at the brachymorphology and compare. So, from now I'd like to move to another issue. Effect of melting fusion of PT, PI, and P, thermoplastic film, interleaved on the flex toughness and film behavior of carbon, fiber, epoxy, thermosetting component. This left-hand side shows the application of 5 reinforced composite. So, yeah, automotive and UAM and aircraft. We prepared the specimen like this. Just before I mentioned about the delamination. Delamination is a big problem. So we have to prevent this kind of delamination. We use the PET, PA to peak. We prepared procedures, and we use the vacuum-assisted resin transfer molding. And finally, we prepared the mode 1 specimen and the mode 2 specimen. This is the result of mode 1. Again, the lead PT, PIP. The situation is like this. In case of a PEI and P, we can observe fiber bridging, nano bridging occurs like this. But the lead and PT, we cannot. We also observe the same image. Lead, PT, PI, P. In case of mode 2, the result is like this. I will skip the details because of time limitation. Mode 2 result, same result, like this. This schematic representation of melt-infused interleaves toughening mechanism. This result is published in Polymer Composites. Incorporating PTPI and PIC film significantly improved the mode 1 and the mode 2 ILFT interfacial flex toughening. And the failure modes in mode 1 were characterized by cohesively failure and predominant intermittent adhesive failure, leading to the tortuous crack path with extensive plastic deformation in PI and PIC interleave laminates. In mode 2, the lead and PI laminate failed cohesively while in PIC laminates, the crack deflected to the weaker TP epoxy interface resin due to its weaker bonding with epoxy than PI and limiting its full toughening potential. This result acknowledges the critical role of matrix compatibility. I'd like to move to another issue. Optimization of interleaved structure with amorphous halloysite nanotube for superior performance of shear-bonded parts. In various environmental conditions, this is a very important thing in our case because we have to apply to the shipbuilding. As you may know, the halloysite nanotube by heat treatment, the microstructure will be changed, right? Over 700 and 1000. The structure from semi-crystalline to amorphous structure. Very important thing. The water layer will be disappeared. specimen, epoxy, nanotube. We prepare the specimen. In case of a pipe composite, we prepare the 5 kinds of specimen. E3 means this, neat epoxy. And E2A1 means 2 layers of neat epoxy and amorphous 1 layer. So we change. We designed like this, 5 kinds of specimen. The result. Flat and cylindrical specimens were made using filament winding on a 400 millimeter mandrel. We call this mandrel. And filament winding. Finally, we can get the 5 composites. Here, heat treated at 80 Celsius for 5 hours. Amorphous halloysite nanotube reduced moisture absorption significantly, with amorphous structure achieving the highest reduction, 190. Here, interleave the structures with amorphous halloysite nanotubes for superior performance of shape RP pipes in various environmental conditions. This kind of all result also is published in Thin Walled Structure. Amorphous halloysite nanotubes significantly reduce the moisture diffusion. Very important thing. Due to their barrier properties, a tortuous barrier will be made, incorporating with the halloysite nanotube. Just to compare those results of fracture stress and strength before moisture absorption, after moisture absorption, after drying. The situation is like this. We can summarize it like this. Before moisture absorption, AHNT composite showed superior fracture modulus and strength. A3 had the highest strength, mean amorphous structure, 3 layers, showed the highest strength. Moisture reduced the fracture properties, but AHNT composite retained higher performance, with showing 30% reduction. Before, after drying, the situation is like this. Morphology change. Also, load and 5 diffraction. All those design structure change like this. This slide shows the relationship between pipe stiffness and before, after drying. The result is like this. So here, as you can see, the most highest value is H3, 0.5 halloysite nanotube, and amorphous halloysite nanotube is the most, showed the most highest value. We check the situation and the flex pattern research result. The first, influence of W by D ratio and E by D ratios on bearing strength and failure mode. Geometry effect. Increasing the W by D ratio significantly enhances the load carrying capacity, with a notable transition from net tension to bearing failure mode beyond the W by D ratio of 1.5 E by D ratio. This is a very important thing regarding geometry effect. And the second, temperature-dependent mechanical properties. CF-pack composites exhibit temperature-dependent mechanical behavior with lower bearing strength at high temperature compared to the room temperature and low temperature. The composites maintain good interfacial bonding without delamination and across all temperatures, showing higher stiffness and lower displacement at low temperature and increased ductility at high temperature. This is the second result. And the third, impact of a nanotube reinforced on adhesive strength. Incorporating just 0.5 HNTs into the PEI adhesive in CF-pack joints significantly improved LS left shear strength due to the enhanced interfacial bonding. However, highest HNT loadings lead to aggregation, reducing left shear strength. Regarding the effect of melt infusion polymers, melt infusion of PET, PI, and PEEK films into carbon fiber composite significantly enhances the flex toughness and the damage tolerance with improvement of up to 284% in mode 1 and 188% in mode 2. Interfacial, interlaminar flex toughness, establishing it as an effective toughening technique. The fifth one is moisture absorption and mechanical performance. Carbon fiber composites modified with amorphous hallocyclone tube exhibit reduced moisture absorption and higher fracture and five stiffness, both before and after moisture exposure. The A3 and E2A1 structures partially demonstrate superior mechanical performance and the shoulder stiffness post-moisture absorption, making them promising for industrial application. Final one. This is the final one. Comprehensive insights from our experiment research for design and optimization. The studies correctively highlight the critical role of geometric parameters, double by the ratio and A by the ratio, temperature effect, and nanotube reinforcement and optimizing the performance of CF-pack composite. These factors should be tailored for high-end structure application, ensuring long-term durability and efficiency in challenging environments. So this is our systematical research. So I concluded finally the comprehensive insight. So thank you very much for your kind attention. my composite family. Yeah, here. From India, Sanjay Kumar, Dr. Sanjay Kumar, and from Kenya. We enjoyed the summer vacation in Korea. Yeah, that's it. Any question? Oh. Yep, regarding your very good question. Regarding your question, one Korean company is trying to make that kind of hydrogen storage. My ex-student is working at the company. So nowadays, by using the filament winding method, they are trying to make that kind of hydrogen storage by using the thermal static composite. No, yes, yes. So how much you can handle the pressure or temperature? Yeah, at this moment I cannot say, but we can overcome that kind of limitation, I think. They are now developing. Yes. So next year, I will organize one international conference in Korea, Busan, AMDP and PEMA conference, combined conference. So your participation will be highly appreciated. Okay. Maybe the end of the June next year, 2026, okay, in Korea, Busan. Okay. See you again in Busan. Okay. Thank you so much.
Great privilege to introduce Professor Siris sir. So, Dr. Siris Sonawane is a distinguished professor in the Department of Chemical Engineering at the National Institute of Technology, Warangal, and currently serves as the Dean for Research and Development, and widely recognized for his profile research output. Dr. Sonawane is the Institute's most published and cited academician, over 230 publications in leading national and international peer journals, and he has also made significant contributions to the field through his editorial work on 8 books and over 60 book chapters. So his research interest encompasses a diverse range of areas, including process intensification, nanomaterials, fuel cells, and wastewater treatment. And Dr. Sonawane has secured significant funding through prestigious projects from agencies and schemes such as Imprint, Spark, Water Treatment Initiative, ISRO, DRDO, MITI, MOEF, DBD, and DST, and has undertaken collaborative research endeavor with international partners in Russia, Tunisia, and Singapore. He has also actively engaged in industrial collaborations, providing consultancy services for over 25 industrial projects. And recognizing his exceptional contribution, Dr. Siris has been appointed as a chair professor for Chiron Life Sciences Private Limited, Ahmedabad. He is a recipient of numerous prestigious fellowships, including Boy Scouts, Erasmus Mundus, and Humboldt, NAVA, and IGSTC Connect Plus, so on. So he accolades further includes prestigious awards such as Hindustan Door Oliver Award from the Indian Institute of Chemical Engineer for excellence in the application of science and technology for rural development. The Vasvik Award for outstanding contribution in industrial chemical engineering research, and Best Faculty and Research Award from NIT Warangal. Dr. Sonavane is an active member of various research and academic societies and has served as a guest editor for several leading journals. So on this occasion, I extend my sincere congratulations to Professor Sonavane and his recent appointment to the General Body of Wetland International South Asia Society. And with these words, I welcome Mr. Dr. Professor Sirish Sonavane sir to deliver his lecture. Yes, sir.
Thank you so much, sir, for accepting our request. So we are glad to have you today. So I would like to invite Professor Pankaj to give a memento to Professor.
Produce, once we have set the parameters, we will have the continuous same quality. Okay? So let us look to that how we can do it. So other things I will just keep it. Okay? I will just see that basically these methodologies, microreactor based one, we can produce. I will say the manufacturing facility will be in a very small room. Okay? I will show some Corning reactor also. They are very small, and you can produce in a very small room all these some per month per tonnage we can produce. There is very important advantage that using this methodology we are getting the products per unit manufacturing is very higher. Capacity you are increasing. Okay, and there is also high yield and selectivity. So one of my student, that whatever the student I work, other things are, you know, definition wise if you see, this is what I want to say. So bigger plants are there manufacturing, even if you talked about this nanoparticle, I will give you one example of conductive adhesive. Recently, I mean on the 10th, I invite you all the people for this technology transfer also. Okay, there is one of my student who has produced the nanowires, and you will get the exposure also today. If you are going to be there in the chemical department during the experimental session, you attend that. So there is a nanowires production, and is going to be used it for the adhesive and epoxy resin. So basically if you see, our plant sizes are quite bigger, but we can have in very small size plant this production it happens. So all these are related to chemical. So 2002 we have this one. By 2025 we will have very smaller space. Why it is? Because as a bigger size, the hazards are very typical. You can see the Bhopal gas tragedy, all of us know. Plant size is larger, methyl isocyanate gas has been liberated, and based on that it has happened. Now this is conventional method, we usually do it scaling up. You can see in the R&D you have this lab, then you have on the pilot scale, again goes to the what it's called the plant manufacturing, correct? So in place of that, on the single plate, for example fuel cell, you know the stack it is, you also get on a single cell also. So you can first make it on the single plate. So let us say it is in a micro reactor, and then you can number up it. So it is very simple. Once you produce into the number of one plate, the same will be on the product onto the number of plates. So it is in a mass production. I will show you the actual scale in that also. Okay. So this is basically the methodology. There are number of reactors are there. For example, micro reactor. So this is one. Capillary if you take, for example, if you see on the backside of a fridge, there are capillaries are there. Different capillaries you will find. Okay. So capillary, what is the advantage you are getting? Basically the surface area is quite higher. Because of that you have the better mass and heat transport. Okay. So basically the flow will be in the laminar, and maybe Reynolds number is maybe less than 500. But the layer distance is quite smaller. Because of that you have the better mixing. If doesn't mixing happens, you have the junctions are there, Y junction and T junctions. Based on the junctions you can have the mixing and goes to the one to the other turn, and then you have this one. So this is the way for the nanoparticles also we can able to produce that. Okay. So let us see how it has been done. So we will go to the micro reactor. So as I told you, it is the dimensions between the maybe 0.1 to 1000. Okay. There is also, it is could be on the flat plate also you have done grooving is been carried out, and from there the material is been produced. Okay. So similar fashion we will produce the using for the nanomaterials specifically for fuel cell. You know, in the fuel cell there is one catalyst is been used, because there is an anode and cathode, it has been coated. Okay, it is a specific catalyst called as a platinum. Okay, platinum is gives you the both the reactions, reduction and oxidation reaction. Okay, it is very unique catalyst, noble catalyst. It won't give the much poisoning. In the carbon black, it has been added in the nano size. Okay, why it is in nano size to be added? Because surface area will be higher, quantity required will be the lesser. So per meter square loading will be, you are bringing down lower. Okay, so this is what the advantage, because platinum if you look, it is very costly, costlier than the your maybe gold. Okay, very costly material. So precursor are costly and the platinum cost is high. So if you produced in the nano size with a uniform particle size distribution, narrow size distribution, it is the advantage. Okay. Now if you produce this particle using the batch reactor, you will have the particle very wider distribution. Maybe wider distribution means some particle will be of, let's say 100 nanometer, some will be 2000 nanometer, 200 nanometer, some will be in the micron size, okay, sub-micron size, and you will have the distribution with the very wider. So because of that, overall performance is going to be reduced. So if I have the range of, narrow range of a particle, I will have the specific surface area, and based on that I will have the better advantage, okay. So these are the basic requirements are there, micro reactor. So we can produce this one in the micro reactor, okay. So basically if we look to this micro reactor significance, it is as a scaling up means small reactor, you will take the reaction in the small what is called flask, go to the bigger size 1 liter, and then bigger in the bigger kettle. So in place of that, it is very simple. You have the number of plates only, just need to increase, okay. You have the playing cards, you can see, you have the playing cards together and one playing cards, right. So all these playing cards is kind of, you can say it is the kind of total what is called numbers, you are making it together, okay. Stacking, we can say, stack, okay. So let us look to reactor. This is a kind of micro reactor, you can see, this is a matchbox, they are really smaller in size, okay. So you can see the, what is called the number of channels, they could be, 1 mm, 2 mm channels are there, okay. Through the channel, the reaction has been happening, okay. So this is one type, okay, stainless steel, I will show you, you can have also your reactor also. This is channel type, you can see it's an acrylic, what is called micro reactor. It is an acrylic, inlets are there, and then the reaction goes and flows through it, and then outlet it will come, okay. So this is one. Capillary I will show you, glass, silicon or others are there, you can see here, okay. Mixing will come and happens, or maybe two will be mixed and then it will come down and then mix, and then product is going to be out, okay. So from Hyderabad, there is one company, it is called Micro Reactor, Chem India. They have this reactor, you can see it. This is also mechanical engineering, you can design this one. Plates you can make it, grooving you can do it, okay. On the graphite you can have, like bipolar plates of a fuel cell, you can see here. So basically the structure is very important. Why it is important? Because it will give you the, the mixing as well as the, residence time required, okay. So here you see, this is T junction. Let's say if you have 3 components, you can add 1, 2, 3, or 2 components you can add 1, 2, mix it, goes here. What is happening here? Splitting. Again mixing, then curve. So number of turns will be there, you have the again mixing, okay. Residence time you are getting more, okay. So like that, it will have the mixing, and then it comes and goes out. I will show you. So platinum catalyst we have produced through this kind of methodology, through this stainless steel, okay. So there is also other techniques are there for fabrication, it is called ligab techniques and other micro machining. Today you are going to see one more reactor, okay. Why I am showing this? Because for there is earlier methodologies, you don't need to go to the chemist or chemical engineer, we can do it ourselves, reactor manufacturing, as well as you can also produce it yourself. You know the mobile glass, what is the mobile glass name is? On the top you have the mobile glass is there, right? It is called Gorilla Glass. Who is the manufacturer? Gorilla. Corning. Okay? Corning technology. Gorilla is a brand name out there, right? The Corning technologies. Corning is in the optical fibers, and that Corning has produced also in this reactor, okay? That is called as a reactor, what is called as an advanced flow reactor, okay?
I will show you how it is useful to produce this nanoparticle production. Okay, iron oxide, then cobalt, nickel, number of other nanoparticles we usually produce. I will show you how it has been useful. Now, why we should go with this kind of reactors? Okay, I have shown you. There is your one structure of that Chem India. What is the structure? Just see. Coming, mixing, splitting, mixing, and then again splitting, and then goes like this, right? Again splitting, mixing at separate place, right? This is one configuration. Corning has done the research with one of the professor in the USA, okay, in the MIT, with I forgot the name of that professor, with the professor Hijar or somebody, I forgot. So in that one, initially they come up with one reactor configuration. Okay, that reactor configuration we will see how it is. Okay, then we will come back. Why I am showing this? Because to make the nanoparticles, these things are very important. Mixing, one parameter. Residence time, second parameter. Why? Particle initiation, nucleation and growth, it will happen. Particle will have the agglomeration. Once it is agglomeration or the unified distribution, these are the major challenges. Practically I will show you how it has been impacting, okay, with an energy, okay. Show you some videos also about the Corning, then we can come back. That is also fine. Okay, we'll see video and then we'll come back so that you can understand. Can you see this? Sorry, I mean, I'm not getting the video. I mean, audio is not there. Ek minute. Otherwise, I have this one. Speakers are there. Yeah.
Is it playing?
Yeah, it's playing. It's playing. Okay, leave it. We will see. I will show you. Can you see this one? Speaker is working. But because of this attachment, the speaker will also not work. That's what the issue is. I will show you later. Okay. Can you see this one? What this structure is? This is all glass plates attached. You can see this heart-shaped structure is there. These are the hearts are there. Okay. And these hearts are connected with the other heart. Okay. Why it is? There will be a mixture, two reactants are coming. For example, let us talk. You want to make a platinum nanoparticles. How you will make? It is required, for example, a fuel cell. How you will make platinum? Chloroplatinic acid you will take, precursor, okay? And then you will add the sodium borohydride, one reducing agent. A plus B gives you C, simple reaction. So A and B, you are adding it, but just adding is not sufficient. It will precipitate out the particle of a platinum. So it should have the proper mixing, okay? And then go to that. So here if you see, goes to the second, third end like this, mixing takes place, goes like this, and mixing happens and then comes out. Okay. So like this is one plate. Okay. Like this you can see that there are number of plates are there. Okay. I will show you. This is the configuration, for example. Okay. Additional through the pumps you are passing through it. Okay. Here you can see these are the flow. You can see over here. Okay. And then reaction it happens and so fast, and then you are getting output. Now whatever other things you are seeing like this round shapes, this one is for the cooling, or maybe if you require heating you can use that for heating. So this is one plate. You can have the number of plates also. This is one plate I talked. Okay, you can have the other plates also. So you can have this mixing. Okay, so you can have this one plate, two plates. Okay. So other things are there. So, okay. Okay. So this is what we have this reactor. Others are also you can have. Okay. Some of the, this is the, for your lab, if you don't have, you can use a syringe pump. Doctors use a syringe pump to pass the liquid, right? So same way you can have this syringe pumps. Okay, attach that syringe pump with this single plate, number of frames. This is only 1, 2, 3, 4 kind of. Now someone say that I required 10 tons per month. The reactor size is different. They are of this 2 feet or 3 feet size reactor plates are there, and then number of plates will be more. In the same hall you can produce that material. Okay. So this is how it is. Now there are also other capillaries. I told you that could be of a glass also. You can see these configurations in my lab. So you can have these reactions and it is going to be happen. Okay. There is also, as I told you, that capillaries, if you look for the refrigeration shop, you will get varieties of capillaries. Okay. From 2 mm, 3 mm, different junctions you can create. Only limitation, it is made up of a copper. You can also have your from the steel. Okay. We can have this one using the other possibilities through here, and you can syringe and pump it. Okay. So I don't want to go in the detail. Now you look, this is steel capillary through which again syringe pump you can produce. There is also possibility that simple Teflon tubes also you can use it, okay, to produce these nanoparticles. As I told you, this is heart-shaped structure for your corning. This is the Teflon helical. Number of coils are important. DIN number varies. Mixing will be there. Number of tons will going to impact onto the overall product. Okay. So you can use the number of cases. I don't want to go in this detail about what it is called biodiesel and other peracetic acid chemical production. We don't want to go. Let us go to the nanoparticle. You have already learned. It is for the top-down approach and bottom-up approach. This is bottom-up approach, and using this one, we can use the micro-reaction. So copper spiral wires, you can use it to produce this particle. You can see the distribution. Distribution is very narrow. You can see here 6 to 18 nanometer size, very smaller in size of iron oxide. Okay. Same using the Corning and AFR reactor. Okay. So space-time, their flow rate, space-time, it is reactor size divided by the flow rate. Okay, V upon volumetric flow rate, volume of a reactor divided by the volumetric flow rate. Okay, that space-time, will be defined, have the two impacts. One is how much flow rate is there and what is the volume of reactor. So that will impact onto your particle size, okay, residence time. So this is again, you can have other zinc oxide nanoparticles. You can see here earlier the sizes are, PhDs are important, as I told you it should be narrow, okay, and with the AFR and reactor configuration also plays very important role to produce this nanoparticle, okay. So there is also one possibility about a nickel. One of the master student, she started working on that. You can try to see the CFD configurations. I think in your department, the Professor Karthik and other people are working on that micro reactors, micro channels actually, not micro reactors, but channels. Same thing it is. Okay. So basically, this nickel particle to replace the platinum, this we can also produce using the micro reactor. Okay. So as I discussed with you, these are the major important things what I want to talk to you. Okay. Platinum and palladium catalyst. Okay. As I told you, these are the very important used into the fuel cell, anode and cathode along with the carbon. It is called XC75, some specific grade is there, okay. That contains the platinum catalyst, commercial grade. We can also produce this one. So our motive, intention was, can we reduce that quantity of platinum? Can we continuously produce that platinum? Or can we use that precursor, what is called liquor, whatever it is formed, directly you can add into the carbon and then make it the your membrane electrode assembly for required for the fuel cell. So this is the Y junctions, and then nanoparticle formations is taking place. Okay, so simple capillary you can use this for the micro reactor. So you can see here, these are very, scale is 100 nanometer. Okay, so the size is quite smaller. Okay, you can look here, 50 nanometers size. So how much smaller? Maybe in a range of 10 to 15 nanometer size. Okay, so the optimization is again made, and then with minimum quantity required we can produce. Okay, so these are with different solvents and with water. Differences you can look. Particles are completely separated. There is no much agglomeration. Smaller in size, very uniform size distribution. Mono disperse is always required, desired, same size. Okay, is always desired, but it is not possible to come. Very few, like an ultrasound cavitation only can give you this one. But this is how we can reach to the narrow distribution. Okay, so for that, using this one, we can have the graphene and palladium and other catalysts. You can coat it and then you can make this sizes. Okay, these XRDs I don't want to go. You can see palladium is also same thing. What is the impact? You can see there are different flow concentrations, flow rate, average size. What is the impact of maybe your NaBH4 addition or this PD4 addition will have the impact onto your overall sizes. Okay, so you can have this different configurations. You can, reducing agents you can use it different, citric acid or maybe ascorbic, and then you can have. In India there are a number of other configurations have been produced. One of the companies there, it is called Amar Equipments. Okay, so they with a National Chemical Laboratory Pune, they developed this reactor. You can see their own configuration is different. Okay, you can see here, this is spiral. Okay, then goes to the mixing and splitting, then again spiral and then outlet. Okay, so it becomes their own configuration. you can have this your own design of a microreactor. Okay. One of the student from NIT Warangal, MTech student, he worked with a Corning initially, then he has started his own company. It was earlier incubated in NIT Warangal. Okay. He is also having his own configuration. Florex is name of the company, I will show you. Okay. Now how they make it commercialize, I will show you the actual plant size of the, for the reactors in the China. Okay. But don't think about the China, we can have our own configurations here also. The example is, it is scalable, that what I want to show you. Okay. So now let us look to some of the other configurations. So CFD studies also, one of a student did it, and you can see that how the mixing is important. For nanoparticle, as I told you, this mixing and concentrations, they are playing major role. Okay. So get the mixing, configurations are important. Okay. So if you have this, what it is called, back pressure zones creations is very important, and this, turns are important. So you will create and then mix it, or maybe coming mix it like this. Okay. So initially you can see here with a different residence time, the mixing and the concentration zones will going to change. You can see here the configuration within a different CFD studies there. Okay. So let us not to go in this detail, because we are not, but this one is the interesting slide. Okay. I will just show you one commercial finals, one slide, then you can understand. You can see it, whatever you are going to see the reactor in our lab, it is this low flow reactor of a Corning. Okay, very small. How much it is here? 5 tons per year. Very small. Number of plates are more. You can produce 2000 ton per year. How much the reactor size? You can see 2 feet, 3 feet. Okay. It is of a G4. So we have low flow reactor, so you can have the scalability is there. Okay. Continuously you can produce this one. Okay. This material. So this is important for this continuous manufacturing. Okay. I have given this example of fuel cell. Let us see how this other student did it, and then we will go to, we'll go to the Prashant slide. Even we can go to the Rajesh slide also later. So that Prashant has did with this platinum production and with a number of other cobalt and other things. You can see here, this Vulcan XC is the grade, commercial grade of used for the carbon support. Vulcan XC 72. Okay. I might have told 76 or 74. Okay. In that one, in place of that, we can use this RGO, but this platinum or maybe nickel or molybdate, we can replace this platinum catalyst, because it is a costlier, so non-noble metals you can replace to use it, this catalyst. Okay. Same way, so we can produce into the this what is called in the microreactor. Okay. Now these are some of the performances are there once we use that catalyst onto the in the anode and cathode. So you can see here, platinum and molybdate both are there. They have been utilized to produce this one. As well as you can see here, there is also 40% replacement is there. Here you can see, these are the platinum catalyst prepared using the microreactor. You can see these are the two important areas are there. What it is called, based on that adsorption and desorption area, it is a cyclic voltammetry graph. No need to go in the detail, but active surface area is improved using this continuous manufacturing. Okay, that's what the intention is. Here is also you can see platinum this nickel is somewhat replaced. So electrochemical surface area you can see here, 26, 14. Earlier it was 7 to 6 to 7, which have been largely been improved. Okay, this area. Okay. So this is one of the advantage when you make this continuous manufacturing. Okay. Now I will show you the one of the study of the student have did it actually. Okay, there is also polymer nanoparticles you can produce for polyalumin using the microreactor, but it's not of your interest. Okay, so it is related to energy applications, you can do it. Okay, so let us look to the other possibility of the Corning. We will go to the so maybe if you are coming, this is one of the possibility. Let us look to the application first, and then we will go to the problem. First look to the problem. See, conductive adhesives generally been used in the flexible electronics. RID is there, there is also it has been utilized. Ink are there, for example, conductive ink is been coated so that you will get an flowing the current through that area. Or maybe if you want to have connect some two components, then you will have this adhesive. So adhesive will contain two components. One is the silver particle and one is the epoxy resin. Epoxy resin gives you the adhesion and silver particle will give the conductance. But problem is that the silver quantity, if you look, it is almost 80% addition and 20% is epoxy. Okay? So these particles of silver, they are the flakes and they are in the micron size particle. So understanding is that can we have the silver nanowires, okay, so that you will have the conductivity, quantity required will be the also lesser, surface area will be there higher, and overall performance will going to be improved. And this is what the current trend goes on in the conductive ink industry as well as into adhesive industry. But the problem is that we should have the continuous manufacturing. It should not, whatever you have added, once you find the nanowires, tomorrow I will get the silver particles only, round sphere. So it should not happen. So that's what I'm saying, that continuous manufacturing has this advantage. You will have the continuous nanowire production. Okay. So let us look how it is been made. So this is, for example, we made within two atoms basically. Okay. For example, you look to the capillary, through stock solution pass through the syringe pump, and there are some of the chemicals and other things are there. You can look to the residence time and reactor, and then you can produce these wires. You can see here some of the residence time, as I told you, they are also very important. Initially you see in the 5 minutes residence time, let's say flow rate is slower, maybe whatever it is given 10 ml per minute, for example, okay, lesser than that. Reactor size is 1 meter. Then you will initially find there is almost a spherical particles only. You increase the residence time, somewhat you can see the length has been increasing. It is not easy to make this optimization. You may be thinking that it is very easy, just add and get it like that. But if you see, it took longer time to optimize this thing. Okay, and then you can have this latter wire generations. You can see here, these are the again temperature optimizations of the reactor. You can see the wire. You can see more detail in the wires here. You can see here these are particles. At what temperature, if you look to this one, you are getting this one. But if you increase one, okay, higher, lower this copper chloride concentration, you will find almost uniform wires. No particle. So once reactor size, capillary length, flow rate, concentration, once it is fixed, I am getting the continuous wire productions only. Okay. So this methodology, as I am telling you, that is been produced, and this it is the student has been going to be PhD student only. Okay. He did it, and he made it own startup now, and he is going to use these nanowires for the adhesive and conductive ink. Okay. So you can see here, these are the optimized length of a nanowires is important. So it will have the better conductance directly, and these are the some of the optimized results are there. No need to go. Now how to scale up it? Scale up will be very easy, as I told you. You want to have more tonnage. I will have the capillary, the different capillaries, and you can have this one continuously you can produce, and the capillary coils will be different. Capacity we can able to produce. It is very slow written here, but actually we can produce in the large quantity. Okay. So in this way, this is somewhat in a conductive ink formulations. You need to be measured in terms of resistance actually. Okay. And this is the ink formulation which contains, you can look to here, almost 70% you can use it. Okay. And maybe 30% nanowires also we can able to width and lengthwise specifications. Okay. So this is what the actual ink shelf life you can have for longer time. Maybe it is giving, these are all the nanowires only, and you have this shelf life, bulk resistance is not much change. It has 10 to 12. Okay. I can show you. This is the, you can see here, screen printed. Screen printing is been used. You can see the screen printing also in the lab. Okay. And how it has been here, you can see this is very small gap, and from there you can see that conductance also, okay, of this nanowire. Okay. So our responsibility is to make it at a large scale, as I told you again, to make it in a ink at homogenizers and other things are there. You can see the bulk prepared ink also in the lab. Okay. So this is one story. So now I will tell you another thing about what you are going to see, another thing in the lab. Okay. You know the atomization process, okay? Atomization process, for example, in the engine, IC engine, you have the atomized fuel, you are putting it in the engine. What is the speciality? You are making it smaller droplet, okay? In nanotechnology also, this droplet size has very much impact on to the structures, okay? This is very important. So we will see, you will also going to see that atomization process, you can use an ultrasound atomization, you will get in a finer droplet. Finer droplet will have the impact onto structures. Let's see that how it is impact, and this is very useful. Okay. So again, we can say not nanowires, but you can say the rods. Okay. They are in bigger in shapes, structure. Okay. You can see here, basically ultrasound are the waves which are about 20 kilohertz, and dogs and bats can only hear this ultrasound waves. Okay. We human being cannot hear that waves. But the interesting thing about this ultrasound, you can make the vibration and you can make the droplet smaller in size. Other chemical effect I will tell you later, but you can look normal atomization and ultrasound atomization. Ultrasound atomization will have the finer in size. So look to the application. For example, I required nanorods, and if I want to prepare it, there is only a sealer method, usually a deposition method it takes, and this deposition is not guaranteed that how whether it will have the nanowires or the particle, because in the formation there is initiation, nucleation and formation, three stages are there, and the particle growth will depends on this mechanism. So to be have, let us look to that how it is being made. Okay, so basically you see the liquid is being passed through this ultrasound generator, and here it is basically liquid. Once it is, there is a small orifice here. Okay, once the liquid comes into the tip of this orifice, ultrasound is going to be already been vibrating. It is based on the piezoelectric effect. Once it start vibrating, it produces the droplet. It is going to be break down this droplet. These droplets are again into smaller size. Okay, so these are the finer droplets you can see over here compared to normal your spray. Okay, or normal atomization, high pressure atomization. This is more finer droplets. Okay, you can also use other methodology that I will tell you later. See, this is how these are the droplets. Okay, what is been done? How the capture the size of a droplet? Is it possible to capture the size of this droplet? How it has been done? You can see here. For example, that is an atomizer. Some of the part, for example, it is in a high shutter speed camera has been attached, like 6,000 frames per second, and micro lens has been attached, and then you can have catch this droplet size, and then you can count. It is called as a Sutter diameter. Okay, so it is interesting that you can grow these nanorods. Okay, with the technique you change, structure will change. Okay, so this is very much important to use this rods actually. Okay, so this is one interesting aspect. Okay, now I will tell you the maybe other techniques are there released later. I think not useful. I will just close this with one commercial scale how it has reached. I will tell you about nano calcium carbonate, and then we will close the session. Okay, nano size calcium carbonate, this is very much we have used it, and we commercially scaled also. My student is doing, he is already doctorate, and one is technology transfer, we did it in Ahmedabad. Okay, so these are the large scale production. Okay, calcium carbonate, where it has been used, maybe you are thinking it is used as a toothpaste or paper. They are very small applications. Major application is a composite. Which composite? PVC cable, PVC pipes. Okay, it contains as a filler. Okay, almost 30%, 25 filler, percent of filler gives the ghost of a calcium carbonate. Okay, and nano size calcium carbonate has a very large demand in what it is called adhesive. Okay, PVC adhesive. So, but problem is that making it a large scale in India, the people are, maybe it's been done in the micro size particle, but scaling up in the nano size is very difficult, because it requires a very specific shape. If you look, the shape is required was in a cubic shape, okay? Cube shape. For the whatever the PVC and other adhesives are required, a cubic shape is required. It is called as a calcite. Cost is very high, 200 rupees kg for example, nano size. Commercially, if you get even 150 rupees kgs also, you get 10 rupees per kg also you get a calcium carbonate. But this is a specialty chemical additive. So it has been using it as a nano size filler, okay? In the adhesive, specific adhesion is there. If you throw that adhesive, it should be attached to the surface, right? Thixotropy should be there. So such a kind of adhesives has been prepared using nano size. So how it has been done, I will just show you. When you go to the lab, you can see this methodology also, okay? It is a hydrodynamic cavitation based methodology. As I told you, ultrasound, you can make it using the hydrodynamic cavitation. You know that pumps usually been used and the 40% of the energy has been lost because of a cavitation. Cavitation was nothing but what? When there is what is called, in the conduits are there, the liquid flows through the conduits. Maybe for example, orifice or venturi, there is a difference in the pressure, okay? So sudden collapse, sudden drop in the pressure will release the cavities or bubbles, okay? They collapse and that releases the energy, okay? That is a very instantaneous process, but it is very effective for the micro mixing as well as generating the radicals, okay? So commercially you can make it this process. So usually calcium hydroxide been added into CO2 gas. Commercially there is different process again, but to be produced into that particular things, you can use it and then you can produce this calcium carbonate, okay? So I will show you, this is somewhat smaller setup for 15 liters, okay, to be produced the slurry, and you can get this calcium carbonate. You can see here, industry doesn't require your calcium carbonate to remain hydrophilic in nature. PVC pipes or PVC industry, it doesn't require the PVC, it should be complete hydrophobic. It should hit the water. If it is have the water moisture content, you will find the patches onto surface. You have seen any PVC or cable or this one with a patches? No, because it has this, made it with a calcium carbonate with a hydrophobic, okay? So you can see here, you can see that as a contact angle, okay? If you put the water drop onto the surface, it will spread, right? If the surface is hydrophobic, it will show the contact angle bigger, droplet, right? Contact will be almost 150, okay? You can see here, and you can see that calcium carbonate difference, okay? Size wise also very smaller. You can see here the how much size is 30 to 41, very narrow size. Almost all the particles are in the range of 30 to 50, let's say. So this is the nano size calcium carbonate. In this way you can have production as a polymer composite. It can be used in pharma industry also, in adhesives also. I will show you some of these in nanocellulose also, one of my student has carried out. And that what I was telling about that calcium carbonate, he has first order, he also got it from one of the company, okay, for to produce this nano size calcium carbonate, okay. So it is on to the trial basis, but 500 kgs is good enough for initial start, right? So there are good opportunities to have a continuous manufacturing. This is not a continuous manufacturing. This reactor is a process intensifying device, okay, whatever I have mentioned. Orifice and venturis, you put it and then you produced it, okay. So it is, gives you the what is called semi-batch kind of thing, you can say, okay. So this is from my side. If you have any questions, okay, let me know, then I can explain you. If you want to come to my lab, you are always welcome. Regarding that platinum, I will show you how the fuel cell is being prepared. So these are the fuel cell, components. Okay. In that one, MEA you can see here. Inside there is a stack. This is a stack. In that one, MEA membrane will be there. Okay. In that one, platinum catalyst has been coated. Okay. So that is in the nano size. Okay. Some other performances are there for you. It's not much interesting. Okay. For you, for the nano size system. Okay. So if you have any questions, let me know. Otherwise, you can shirish@nitw.ac.in. Okay. You can contact or you can come and see in the lab now. That will be, you can talk with my students. Okay. You can see what they are doing. If you need a nanocellulose, you can come work with them. You can want a calcium carbonate. Yeah.
Sir, can pressure and time can affect the morphology of this nanocell?
Yes. Yes. Specifically, time will affect. Pressure doesn't have the much impact, but time has the very impactful. Okay. Because with the pressure, basically your flow rate will change. So it has ultimately the impact on that one. Okay. That's what we did it lot of optimization for nanowires. Just changing the flow rate, just changing the concentration, time, temperature, and the capillary length also. It has the impact. So once it is finalized, then it will be easy. You will get that almost in the same size. Okay. Yeah, different kind of morphology, yes. You can do it. It depends on which material again you need to do it. Okay, for all you say that nickel nanowires I want, then again I have to see the precursors type, concentration, and then but for silver nanowires you can do it. Okay, you can have your own configurations, you can start working on that. Okay. So there is what is called, I forgot the name. Bharat Cement is one of the major cement industry in South India. His son is there, He has started recently Bharat Semiconductor, I think. Okay. In that one, you people also have mechanical engineers have the opportunities. You can think about, preparing this thermal insulating materials. Or these composite related to that, okay, for the batteries and electrolyzers also. Electroplating cathodes and materials has again the new demand of material. You can think with that, okay. So your question was definitely it has to be, as see the atomization again has the different conditions. Residence time orifice change, surface tension also has the impact, density has the impact. So it will be going to change based on this parameter. Okay, just orifice size, for example, say it is called as a capillary number, as well as density, surface tension, they are majorly impacting. Okay. So hydrophobic nature will have also impact. Okay. So it will impact on the droplet size. It will impact on to particle size. Okay. Because reaction is also kind of what it is called, everything, there are phases are there. Growth is taking place, death is happening, particle remain stable, they are agglomerate, they will come together. These all different mechanisms are been happening in the reaction. So the same thing in the microreactor also will have. Okay. So these are being impacted by the other parameters, right? Temperature, pressure, and velocity, flow rate, residence time. Okay. Okay, then you can go and see in the lab. Okay. I have one meeting. Okay. But I will join after that. There is also fuel cell and other things. You just go and look and see that one, and later you can have. Okay. Thank you very much. Okay. Thank you. Yeah, you have a question? Yeah.
Use and microchannels
Glues and?
The grooves and micro channels.
Yeah, for the fuel cell you are talking, it has been done with a CNC machine, very specific. Okay, with a graphene CNC machine, we given the design. Mechanical engineering, you are that old batch student only. They did it with my student, and it was done. These are from, we made it actually in Nasik. We given for the grooving for polar bipolar plates. Okay, you can do that grooving now. Is available. Okay, try to see that you people try to file the patents. You can have your own methodologies, technologies. Okay, make it. It's possible is there. Everything you can have. You know, if you want to have startup with this, our innovation center is there. We are going to fund also. Okay, so my student has got going to be got the funding. He has got this Ajanta Pharma. He got mint chocolate or mint some tablet is there. In the tablet they are adding that calcium carbonate to have better performances. So they want a nano size. So that got the order of 500 kgs. Okay. So manufacturing cost hardly whatever you use it doesn't go more than 10 rupees, 12 rupees per kg. Later he can increase the cost. You can understand. So one of the Florex is one company startup of my student. He gives the demonstration of that micro reactor only. He has his own configuration. Pune it is there. You can go through it. Florex. You can go through the Google also. Florex is there. FLOWREX, Florex. Okay. One demonstration he charged 2 lakhs rupees. Just to demonstrate 1 hour, whatever in 1 day demonstration. Sorry, 1 week. For whatever you have the chemistry, you do it for 1 week. Whatever you want to use it in 1 week, you do it. It takes charge 2 lakhs rupees. Okay. So you can imagine that in 12 months, even he remains empty for whole 6 months. Still he will earn good money. Right? Even in the half months, he doesn't do anything. Even if you get 2 orders per month, okay, so 4 and 48 lakhs rupees, nothing much, right? Everything is costing, everything you let 20, 30 lakhs rupees is easily can earn, right? And he has very big, our seminar hall complex is there, like 2 floors in the big industry is there, okay? Pass out in 2013 or 14 only. Today is 24, 25, I mean 10 years he established that. What is that? What? Process intensification and microreactor technology. Okay, all glass based, all AFR based reactors. Okay, so you can think it. It's not like we people are making the differentiations that we are chemical, we are biotech, we are mechanical, we are metallurgy. Practically, if you see, is all interdisciplinary requirements. Industry is not working. You solve my problem. Whatever engineer is, you are not asking about that. Correct? So linked into that and have a good,
Try to see that whether you are getting possibility to connect with him. Try to go in their lab, work with them 1 week. If you get an opportunity, even paying the money, you go. Don't bother. ESK and other things they will support for your travel and other things. Try to, even now also you can interact with them. Like that only Koiker went. I also went and we got the opportunity to stay there also. Not about talking about. I went to Germany and other number of things. We also went. Koiker is speaking now within a Japanese language. Both are talking in the Japanese. Right? So this change you can make it when you are getting the proper connect network.